All right, welcome to The Explainer. Today we're going to talk about a really clever piece of old-school engineering. You know, the kind of thing that prevents huge electrical disasters. We're going to break down the three-point starter, a device designed for one crucial job: taming the massive surge of power that comes with starting up a DC motor. So let's just jump right in, because this really gets to the core of the problem. You have to ask, why do you even need a special starter for a DC motor? Well, trying to fire one up directly, it's like blowing up a dam. You get this absolutely massive, totally uncontrolled flood of electrical current all at once. And when I say massive, I am not kidding. We're talking about an initial surge that can be 10, even 20 times the motor's normal operating current. Think about that for a second. That kind of power, even for a split second, is just unbelievably destructive. So why? Why does this happen? Well, it all comes down to the motor's own built-in defense mechanism, which just isn't awake yet. See, as a motor spins, it also acts like a little generator. It creates its own voltage that pushes back against the power supply. We call this back EMF, or electromotive force. It's like a natural brake that keeps the current in check. But here's the catch. At the very moment you flip that switch, the motor isn't spinning, right? It's at a dead stop. So speed is zero, which means back EMF is zero. There's literally nothing holding back that flood of current. And the damage? Oh, it's just catastrophic. All that current generates so much heat, it can literally melt the insulation right off the wires. The mechanical stress? It's this incredibly violent jolt of torque that can snap a solid steel shaft clean in two. And on the electrical side, you get this crazy sparking at the commutator that can just completely destroy it. It's a perfect recipe for a very expensive, very dead motor. So to stop this from happening, engineers came up with this really elegant solution, and we're talking over a century ago. It's an ingenious device designed to safely and kind of gently walk the motor up to full speed. I mean, it's just a beautiful example of problem solving, a completely mechanical answer to a really tricky electrical problem.
All right, so let's pop the hood and see what makes this thing tick. We're going to look at the anatomy of the starter, all the key players.
Okay, so here's a look at the circuit diagram. You can see all the main components right here. You've got the big manual handle that the operator uses. Then there's this bank of resistors. That's our current limiter. You see the powerful spring? It's always trying to pull the handle back to the off position. And then you have these two super important electromagnets, the no-volt coil and the overload release. You can kind of think of these as the starter's brain and its bodyguard. And you know why it's called a three-point starter? It's literally because of these three connection points, these terminals. It's pretty straightforward. L is for the main power line coming in. A is for the motor's armature, you know, the bit that actually spins. And F is for the field winding, which creates the magnetic field the armature spins inside. Each one has a very specific job to do. Okay, so we've seen the parts. Now, how do you actually use this thing to start the motor safely? Let's walk through the startup sequence step by step. So this is a totally manual process, right? It all starts with the operator physically moving that handle over to the very first contact point, which we call a stud. Then they slowly, and I mean slowly, move the handle across the rest of the studs. Once they get to the final run position, a little electromagnet kicks in and holds the handle there so they can let go. Now, that very first step, moving to stud 1, is absolutely critical. The second that handle makes contact, it completes two circuits at once. The first path sends current to the armature, but it has to go through all of those resistors first, which keeps the current nice and low. The second path sends full power directly to the field winding. This creates the strongest possible magnetic field, which gives the motor the maximum oomph, the maximum torque, to start turning. Even with that limited armature current, it's brilliant.
Okay, so as the motor starts to pick up speed, remember that back EMF we talked about? It starts to build up, creating its own resistance to the current. As that happens, the operator can safely move the handle to the next stud. Every time they move to a new stud, they're cutting a piece of the external resistance out of the circuit. This lets a little more current in, and the motor speeds up a bit more. It's this beautiful, delicate dance between the operator removing resistance manually and the motor creating its own resistance internally.
But this thing is more than just a starter. It's also a protector. It has these two built-in guardians that are always on watch, the NVC and the OLR.
These two protectors are really clever. First, you have the no-volt coil, the NVC. Its main job is to act like a magnetic hand, holding the starter handle in the run position. But if the power goes out, the magnet switches off, and that spring we saw earlier instantly snaps the handle back to off. This is huge because it prevents the motor from suddenly trying to restart at full power when the electricity comes back on. Then you have the overload release, the OLR. This thing is constantly monitoring the current. If the motor gets jammed or is working too hard and starts drawing way too much current, the OLR's electromagnet gets strong enough to trip a little lever. And what does that lever do? It shorts out the NVC, which lets go of the handle, shutting everything down before the motor can burn itself out.
Now, for all its genius, the three-point starter isn't perfect. It actually has one major flaw, a kind of conflict of interest baked right into its design.
All right, and this is where things get a little weird, a little counterintuitive. To get a DC motor to spin faster than its normal speed, you don't give it more power. You actually have to do the opposite. You have to weaken its magnetic field by reducing the current going to the field winding.
And here's the problem. Remember that no-volt coil, the safety magnet that holds the handle on? Well, the way it's wired, it's in the same circuit as the field winding. So the very same current that creates the motor's magnetic field is also the current that's powering the safety magnet. See where this is going?
It means that if you try to get the motor to run really fast by weakening that field current, you're also weakening the safety magnet. If you weaken the current too much, the NVC gets so weak that the spring just overpowers it and snap, the handle flies back to off. The starter's own safety feature shuts the motor down, even though there's no actual fault. This exact problem is what led to the next step in the evolution of starters, the 4-point starter. And its solution was so simple, it's brilliant. Engineers just gave the no-volt coil its very own separate connection to the power supply, a 4th point. This completely disconnects the safety circuit from the speed control circuit. Now, the NVC's holding power is totally independent of the field current, which means you get a full, unrestricted range of speed control.
So, when you look at it, the 3-point starter really is a masterclass in electromechanical design. I mean, it solves a huge, dangerous problem with just springs, levers, and magnets. No silicon chips in sight. But you have to wonder, in today's world of advanced electronics, is this thing just a relic? Is it obsolete? Or is there something timeless about its design?
So let's just quickly recap the big takeaways here. First, its whole reason for being is to solve that huge starting current problem. Second, it does this with a simple, hands-on, gradual process. Third, it's got those 2 brilliant layers of protection built right in for power loss and overload. But finally, its big Achilles heel is that flaw, the fact that you can't really control the motor's speed without tripping the safety system. And that, right there, is what pushed engineers to come up with something better.
And yeah, today we have electronic soft starters that are way more precise. But there's something to be said for the rugged, almost foolproof reliability of this purely mechanical device. It really makes you think, doesn't it? In our world of complex code and microchips, what can we still learn from a design that is smart just by using the basic laws of physics? Something to chew on. Thanks for tuning in.